current slide. Turn on the projector. And I have...
It's linear algebra today, right?
Yes.
Okay.
Today's Thursday.
In multiple classes, it's hard to keep track.
Today's Thursday. It must be linear algebra, right? Okay.
Yeah. So that's on my ebook. Because I've got one, I've got the differential equations book in text and linear algebra.
Right. Right. And did you get the codes for both of them? I don't know if you need them.
I didn't do it through MTH Unlimited. Didn't have enough books to justify it.
Right.
So just to go check for.
But you got the ebook without needing the code.
No, I just went to check and looked up the code. I didn't get it from St. Age's websites.
Okay. Well, I finally got codes from WebAssign Cengage, so I put them out there. So
Check it available to rent for $15. So I was like, okay, just do that.
Okay. All righty. Now, there is the announcement about Alabama A&M having the North Scholarship package and stuff like that. So if you're interested in that, please follow up on it. You got the email as well as I did. But the other announcement, and I don't think this will pertain to you any because I don't think you usually come by on Fridays, but normally on Fridays, I'm on the Birmingham West campus. I have office hours from 8 to 12. Tomorrow, I've got to make up the class because last Tuesday, I had a doctor's appointment at 8:40, but I had to be there for labs at 7:40, so I could not be here anytime for my 8:30 class. I was either waiting for the doctor or in the doctor's office or driving back from the doctor, so I missed the whole class. So they decided this morning, first time we've met since Tuesday, to let's make up the class tomorrow. So I'm going to be on this campus from 8 to 8:30 tomorrow morning, and then I'll be making up the class in this classroom from 8:30 till 9:45. Now, after that, I hope to remain on this campus and get some work done, but if we have a meeting or some other reason I have to go to the Birmingham campus, then I'll be going back there. I know at the end of the day I'll go back there because I've got to turn in some paperwork. So whenever they need me back there, I'll go. Otherwise, I'll stay here and work until I go. Okay. So, any questions before we pick up and go here? All right. If not, we had talked about the identity matrix. And for some reason, I did not make a mark where we left off. I think we're at the top of page 56. Does that sound right? Yeah, because we had shown if AC is equal to BC, that doesn't mean that A is equal to B. We showed that one. So I think we're at the top of page 56. Does that seem right?
I think so, but I can't see.
You can't get it because of the internet? Yeah. Okay. All right, that's one problem with ebooks then. You got to have internet to get it, and unfortunately today we don't. So here's where we'll pick up and go from. Top of page 56 is a theorem, and it's one of, you might say, two properties of an identity matrix. If A is a matrix, oops, let me get my pen set up. Okay. A is a matrix of size m by n. Well, let me just say an m by n matrix. Oh, wait. Here's Tyrell.
The one and only.
Well, let's hope anyway. Okay. I didn't say that, did I? Not out loud. Okay. So if A is an m by n matrix, the following properties are true. First, if you take the matrix A, an m by n matrix, and multiply it by an identity matrix. Now tell me a couple of things about identity matrices. A couple of things that are always true about identity matrices. well, no, not M by N. They're always, see, y'all don't know. I have an older brother and a younger brother. And when we were young, and he was going into his adolescence, I guess, or whatever you called it then, he was the wild child, my younger brother. And he considered me an L7. Y'all ever heard that? If you take an L and put a 7 with it, what do you have? A square. So he considered me a square. So that became, his name for me was L7. And after that, he just started calling me L. So to this day, every now and then he'll say, hey, L, you know, not Charles, but L, okay, because of that. So that's what that was to be. Identity matrices are always square. Never rectangular, always square. They've got to be. Now, so if A is an M by N matrix, what size must N be? So see, with an identity matrix, all you need is a single subscript. You don't need an M and an N because they're the same. So what size would I have to be if you're going to multiply A times I? It has to be square. Identity matrix has to be square. So it's going to be, I'll narrow it down for you, either an M or an N, but it can't be both.
So it has to be two of the same.
Okay. Identity matrix is always square. This A is not square. This is an M by N matrix. A is. And if you multiply it by I has to be a certain size. What size? Say again?
N by N.
Okay. I thought I just said I has to be square. That means it can't have two different dimensions. It's either going to be M by M or N by N or I by I or Q by Q, but it's got to be the same. The question is, which does this have to be? Okay. To multiply two matrices, A, we already said, was an M by N. So what size does I have to be to multiply? An N by N, because the two middle have to be the same, right? Okay, so this we just say is I sub N. Okay, now that sets up the problem. What is that product of those two? Okay, it will be an M by N, you're right, but what specifically will be the product? And let me hint you on the name of the I matrix, the identity matrix. So guess what your answer is going to be? A. That's the M by N matrix that's the answer. Because the identity matrix is just like multiplying by the number 1. If you multiply 7 by 1, you get 7. If you multiply N by 1, what do you get? N. Okay? Same thing here. If you multiply A times the proper size of an identity matrix, you're going to get A again. And that size has to be the N matrix. And Muhammad is here. Okay. What's that? Oh, not just in spirit. Okay. Okay, he left his spirit at home. Okay. All right. So that's the first of these. Now here's the second of these. This also has to be true. If A is an M by N matrix, the following are true. There's the first one. The second one, what if I were to multiply I by A? Now, the first question I have for you, what size would I have to be?
Would it be the same as the A?
Would it be what?
The same as the A because it has to be square, right?
I has to be square. A is not square. So what size would that I have to be? Second.
N by N.
Okay. Let's see if that works. If this is an N by N and A is an M by N, do you think? Huh?
They need to be N by N.
Yeah, it has to be M by M. And since it's square, we don't need to use both letters. We just say an M, I sub M. So in order to multiply, if you multiply on the right, it has to be a small or a different size identity matrix than if you multiply on the left, if A is an M by N. So these are not the same I's. They're different size I's, but they are. And what would your answer be then if you multiply I by A? The right size I by A. It will be an M by N, you're right. But I'm asking what will be the answer.
A.
That will be A, exactly. Okay? Because the identity matrix is just like multiplying by 1. It does not change the value of the other matrix. Okay? All right, so let's do example 6. All right. Here is a matrix. 3, negative 2, 4, 0, negative 1, 1. We're going to multiply this by an identity matrix. What size identity matrix does that have to be? What? 2 by 2. Is that what you said? Or you said 3 by 3?
2 by 3.
2 by 2. It does, because this is a 3 by 2, and you have to multiply. So tell me what the 2 by 2 identity matrix is.
0, 1.
No, it isn't.
1, 0.
Okay, 1, 0,
0,
0, 1. Perfect. And let's multiply. Okay? What will your answer be?
It will be maybe 2 by 2. No. 2 by 3.
2 by 3?
Yeah.
2 rows, 3 columns.
No. 2 columns, 3 rows.
Okay, that's a 3 by 2.
3 by 2.
Okay, always row by column.
Yes.
Okay, so it'll be a blank, 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 blank. Okay, the last one sort of ran into the thing. All right, the first entry, what's its address?
Is 1, 1.
1, 1. So what do we do?
2 times 1.
Right?
Equals 1. And it's a row then column. Yeah. And then 0 and 2 is going to be just 0.
Okay, so what do you get? 3. Perfect. Next entry?
Next entry is 1, 2.
1, 2.
0, and then it was negative 2.
-2, is that what you said? -2. Perfect. Next?
We got 2, 1, yeah.
Mm-hmm.
2, 1. We have 4 and 0. So we got
4. Perfect. Next?
we have 2, 2, 2,
Mm-hmm.
2, 2.
2, 2.
And that gives us
Right.
0 times this 4, 0.
0. Okay. Next?
We have 3, no. Yeah, 3, 1.
3, 1.
We got negative 1 and 1 gives us negative 1. And then 1 and 0 gives us
What you get?
negative 1.
-1. Perfect. Next?
Whereas that will
All right. He didn't do it, but it will be 1. Okay. And the reason is -1 times 0 is 0. 1 times 1 is 1. Perfect. And what do you notice that is? It's the same as A. Identically the same as what you did. Anytime you multiply a matrix, any size matrix, by the proper size identity matrix, you're going to get that same matrix again. Always. That's what identity matrix does for you. All right. The next one, the B one here, I'm going to multiply by this.
Would the identity matrix be would be just one less row of the first matrix?
Yep. Okay. What you do is, if the identity matrix is multiplied on the right, it has to be the number of columns of the other matrix. Doesn't matter what the row is, number of columns. If you're multiplying the identity matrix on the left, then it has to be the size of the number of rows of the thing on the right. Because the second here has to equal the first here. So the second is the number of columns, unlike what you like to do. Okay? So the number of columns, that will determine what size here. And if you multiply identity matrix here by something here, then it has to be the size of the number of rows, because it's square. So it's n by n, and then this has to be an n by something else. The number of rows must equal the dimension of the other. So here's a negative 2, 1, 4. That is a matrix. It's called a column matrix or a column vector. And I want to multiply this by an identity matrix. What size would it have to be? Yes, it has to be square, and it has to be 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. What are those elements of that? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? And what would be the result of this? How big? What size? It's what? One row is not a row. That's a column. Okay. Yeah. Your spirit was saying column, but your mouth was saying row. Okay, yeah. It would be a what size? Okay, right. Okay. Okay, so what will it be called? What size?
1 by 6.
A what?
1 by 6. No, 3 by 1.
3 by 1, all right, 3 by 1, okay. Because this is a 3 by 3, multiplied by 3 by 1, and that will give you a 3 by 1. So it'll be 3 rows, you got me saying it wrong now, and 1 column. Okay, so let's go to town with it. Yes?
Is for the first matrix, you just treat that first one as 1, right?
What? No.
That one right there, the first one. Yeah.
Yeah, that's not identity.
Just treat that one as 1, right?
Yeah.
All right, so rather than going through it, it would be the same thing, right? Negative 2.
It better be.
Oh,
yeah.
I got it.
So you say it's going to be negative 2, 1, 4, right?
Right.
It's not hard to check, is it? Just do it. Negative 2, 0, 0. That's negative 2. 0, 1, 0, 1. 0, 0, 4. Yeah, that's exactly right.
So it doesn't matter how big the matrix is, as long as if it's an identity matrix, it'll equal.
No, it does matter how big it is. It has to have, this has to be the identity matrix for the size of the number of rows there. This has to be an I3.
Okay.
If that was an I4, you can't even multiply. If it was an I2, you can't even multiply. This one has to be the same number as the number of columns. It has to be an I2. If it was I3, you can't multiply. If it was an I1, you can't multiply. You know, you got to have, if you're multiplying a matrix by the identity matrix on the right, then the identity matrix has to be the size of the number of columns here, a 2 by 2. If you're multiplying on the left, it has to be the size of the number of rows here, 3 by 3. Yeah. Okay? That's the point. Yeah. The size is determined by what you're multiplying by. Okay. Now, here's a new concept, and we do use it a little bit, but it's sort of like they just throw it in here because they seem like a good place to throw it in. And I don't know why, because we haven't been doing it, but they're going to throw it in here, and here's what it is. For repeated multiplication of square matrices, in order to multiply a matrix by itself, it's got to be square. Because you can't do a m by n, by another m by n, because the m's and n's aren't the same. So the only way you can repeatedly multiply a matrix by itself is if that matrix is square. Okay? So if you have one matrix, square matrix here, multiplied by itself, which is also a square matrix, then you can multiply that and get the same size square matrix. And then you can multiply it by itself over and over and over. Again, it has nothing to do really with the identity matrix, a little bit, but they just threw it in here, okay? So repeated multiplications of square matrices use the same exponential notation that we did for real numbers, okay? So if you just have a to the first, that's just a. That's just the matrix A. But a squared would be the matrix A multiplied by the matrix A. And again, they've got to be square to do that. You can't do it if they're not square. Okay? So for any positive integer k, a to the k is a times a times a times a dot 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 times a, where you have k factors of a. Okay? That's what we mean by a matrix raised to a power. Okay? Now, this is bizarre, but we do it because we do it in numbers too. A to the 0th power is just the identity matrix of that same dimension, I sub n. It has to be square. Of course, all identity matrices are square. Where A is a square matrix of order n. Okay? Now, not just that, here's a couple more properties. If you have A raised to the ith power and multiply that by they did jth power, okay, and multiply that by A to the kth power, where are you taking these? Oh, downstairs. Oh, lower part. Okay, that's fine. I just thought if you were up here, you'd be closer and wouldn't have to walk as far, but that's up to you.
How about the office?
Huh? The office or the room next door, either one. Okay, let me find the next one for you. There it is. Okay. Okay, so if you're multiplying the I to the j times I to the k, A to the j times A to the k, that would give you A to the, guess what? J plus k. Same as it did for powers. If you multiply b cubed times b to the 4th, that would be b to the 7th. Because you have 3 b's here and 4 b's there, that would be 7 b's. B to the 7th. Okay. All right. And then similarly, if you had A to the j raised to the kth power, anyone remember what that would be? The what? Jk. Yeah, multiplied. You add them when you're multiplying, you multiply them when you're raising to a power. That's what you do with exponents. Okay. Where j and k are non-negative integers. We don't deal with negative integers in matrices. Okay. So, let's go to, now you might think there was an easy way to multiply. There's not. these rules seem pretty easy, but to actually do the multiplication, you got to do the multiplication. Okay? So here's matrix A. Thank goodness they gave us a, it has to be square in order to multiply multiple times. So it's 3, no, it's not, it's 2. Two negative 1, 3, 0. Okay, that's your A. For that matrix, it says find A cubed. All right, how do you do that? It's what? 3 times, you got it. 2 negative 1, 3, 0. 2 negative 1, 3, 0. 2 negative 1, 3, 0. Okay? You want to do that first? Okay. What size will this be? 2 by 2. What will the first entry be? Okay. 1. What you say?
It was wrong. I got it wrong.
Alright.
Yeah, it is. Because it's 4 and then negative 3. So that gives you, yeah, it would.
Okay, good. Okay, next.
1, 2. So you got negative 2 and 0, so negative 2.
And what do you get? Negative 2. Next.
We have 2, 1, so we have 6 and then 0 to 6. And last one will be 2, 2. So we have 3 and 0 to negative 3.
Negative 3, right? All right. Now multiply it by itself again. 2 minus 1, 3, 0. What size will this be? 2 by 2. First one.
2, and then 3 times 6 is
What's it say?
3 times 6 is 18, 18 and
Okay. Okay. Explain to me what you're doing again.
I'm doing, I'm sorry, it's 2 times 6. Okay, so 1 times 2 give you negative 2 times 3 give negative 6.
All right.
Negative 6 times 2, negative 6 and 2 give you 4.
Negative 4. Okay. All right. Negative 4. I think he's arguing with his spirit a lot today. Okay.
Yes.
Okay. Next.
Next is going to be 1, 2. So negative 1. Then 0.
Negative 1. Is that what I heard? Okay. Next.
We got 2, 1, so we have 12. And we have negative 9. So then we was 4. No. 9. 3.
3. Is that what I heard? Okay, good. Yes, I agree. Next.
We got 2, 2. So we have negative 6 and 0 is negative 6.
Is what?
Negative 6.
Negative 6. All right. Good. All right. That's your A cubed. And there's no shortcut. There's no identity. There's no anything that would let you know, well, that's what it is. You just have to do it. Okay? So therefore, I wondered why in the world they... Oh, let's see what they got. Negative 4, negative 1, 3, negative 6. Perfect. All right. Now, that little blurb was in there, and now they go back to doing things we were doing before. So let's, I was so wishing that in my 15 minutes between classes, I'd have a chance to eat a granola bar and maybe drink a little bit of Coke because I was so stinking hungry. But I didn't get a chance to. So I'm starving up here, but let's see. Yeah. All right. Let's do, we just did example 7. Theorem 2.5. Number of solutions of a linear system. It seems like we've done this before, but we're going to do it again. For a system of linear equations, precisely one of the following is true. All right. Only one can be true. One possibility is the system has exactly one solution. The second possibility is the system has infinitely many solutions. Okay, and the third possibility is the system has no solutions. Okay, I thought we had hit those before. I know we did with systems of equations. That's what we're talking about here, and they were all linear equations, but here we hit them again, so they throw them in here again. Now, the reason they do is they use a proof here, and I'll let you go through the proof to your heart's content. Now, there's a little discovery here on the top of page 57, and sometimes these are good and sometimes they're a waste of time. I don't remember what this one is. Oh, let's not do that yet because we haven't done what a transpose of a matrix is. Excuse me. The transpose of a matrix is formed by writing its columns as rows and its rows as columns. So let's say we have a matrix A, and it's going to be a very generic one, A11, A12, A13, dot, 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 A1, N. A21, A22, A23, dot, 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 A2N. A31, A32, A3N, my writing is getting worse and worse. That's 3, dot, 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 A3N. Wait, let me just do a dot, dot, dot here. Get down to AM1, dot, 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 down to AM2. Oh, goodness. Yeah. Dot, 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 this down to AM3. And then we'll do a dot, dot, dot all the way along here. And we wound up with the last entry, AMN. Okay, I'm sorry, my head is just driving me nuts right now. I don't know if it's coldness or what, but I can hardly talk. All right. This, by the way, this A is an M by N matrix. M rows, in columns. Okay. Now, since they said the transpose of a matrix is formed by writing its columns as rows and its rows as columns. So what we call A transpose, that's A with a T raised up there, not a number like we were doing before, a transpose here. Here's what that would be. From that A, what was our first row becomes our first column. So we'll do A11, A12, A13, dot, 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 down to A1N. And the next row would have been the next column. I'm sorry, the next column was what was our next row. A21, A22, A23, dot, 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 A2N. All right, next would have been A31, A32, A33, dot, 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 A3N. All right, the pen is dragging a little bit, so let me clean that up just a tad. Okay. I have seldom felt worse. I mean, I don't know what's going on here. Okay, then we're going to do a dot, dot, dot across here until we get to our last row. That will be our last column. That will be an A sub M1, dot, 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 to an A sub M2, a dot, 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 to an A sub M3, and then a dot, 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 a dot, 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 everywhere, a dot, dot, and this will be an A sub Mn. Okay? And then there will be a dot, dot, dot across there. Now, I was writing those rows as these columns, but you'll notice also these columns became these rows. Okay? That first column becomes the first row. Okay? So that is what we mean by a transpose of a matrix. Okay? Now, there's a reason to do these. Not a very pleasant or good reason. I mean, there is a good reason. There's no math involved. It's just keeping up with the bookkeeping. Okay? Just changing rows and columns. And you might say, why would we mess with that? Oh, and if that one was an M by N, this one becomes an N by M. Because now the number of rows is N and the number of columns is M. So it has changed the size. Okay. Now that you know what the transpose of a matrix is, we're going to go back and do the little discovery here. Okay? So let me clear this out of the way. Hopefully you can remember it while I'm clearing it. Here's an A. 1, 2, 3, 4. Very creative matrix. Okay. Here's a B. 3, 5, 1, negative 1. Excuse me. Wow, that hurt. Now, they want you to calculate three things. The first one's going to be A, B, transpose. Now, before you can do the transpose, you have to do the product. So let's first do AB. Can you even multiply those two? Yay or nay? Yes, yay. Okay, because they're both square, and they're the same size as square. 2 by 2 by 2 by 2 is going to give you a 2 by 2. Okay. Okay. All right, let's test 3. We have to find test 4. Okay. Alrighty. All right, let's multiply those two together and see what they get. What size will the answer be? Did you answer that before? 2 by 2. Okay, first entry will be 3. Did you get an answer? Oh, 5. I can't hear. Okay, that would be a 5. 3 plus 2 is 5. Okay, next. Three. Okay, got it. Agreed. Next. Okay. 13? Yes. All right, next. Got it. Okay. Now they want AB transpose. So AB transpose would be what? Say again? Yeah, transpose AB. No. Transpose AB. There's AB. Transpose it. What would that be? First entry. 5. Where? Where do you put the 3? To the right? You interchange the rows and columns. That's what a transpose means. What was a row becomes a column.
So 5, and then under will be 3.
Under it a 3, right.
Then you have
13.
13.
Perfect. So there's AB transpose. There's AB. When you transpose it, you just swap rows and columns. Okay, that's the first thing they ask. Then they ask you to do A transpose B transpose. So let's do A transpose. What would that be?
A transpose will be 1.
Okay, 1 I would buy. 3 over here, okay. 2 and 4. Okay, let's do B transpose. 3 I buy. Oh, here's Daniel. Just a minute, let me do a mark. I'm so hungry. Okay, 3 I got in its place. What's next?
Next is 1.
To the right? Okay. 5. Negative 1. Okay. Then they want to do A transpose B transpose. Multiply those two together. What's that?
How they doing too much?
I can't hear you.
How they doing too much?
Oh yeah, I know. But it's a 2 by 2, so it's not that hard.
They're asking for too much.
No, when they start asking about 15 by 15, that will be too much, yes. Okay. So what will you, by the way, that will be a 2 by 2. What will be that first entry?
First entry would be 1 and 1.
Right?
So first row, first column, AB, okay. So it's going to be 3 and 3 and 3, so give 6.
Okay, how do you do that?
it's A is up top, B is down, so it's 1, so it's 3 and 15 give us 18. 18.
Okay. 18? All right. That will be an 18. Okay.
The next one first, second. Okay, it's 1 and then -3, so you got -2.
-2? Okay. I had it in my head a minute ago, so that'd be 1. Yeah, -6. That's right. Okay. Next.
So we got 6 and
How'd you get 6?
we got 2 and 3, right?
What's that?
We got row 2, column 1. I did row 2, column 2. So row 2, column 1. So we have 3 and
Oh, wait. No, your 6 was right. Okay. I'm sorry. Go ahead. Your first entry was, your first product was a 6.
6 and 6 and it was 6 and 20.
Yeah.
So it was 14.
6 and 20.
Oh, it's not 6 minus 1. It's 6 plus 1.
Yeah.
So it's 26.
26. Got it. Next.
Use row 2, column 2. So we got 15 minus 4.
Right.
No, 10 minus 4.
Okay, wait. How did you get that first one?
Row 2,
Row 2.
column 2, not row. I did row 2. That's what
Let's not do that.
it's
Let's not make up new rules.
row 2, column 2. So it's gonna be 2, -4, I give us -2.
-2. All right. I sure hope so anyway. All right. Here's another one they want us to do. Let's do B transpose times A transpose. That would be 3, 1, 5 minus 1 times 1, 3, 2, 4. What would that be? Anybody? Anybody? We're doing B transpose times A transpose. There's B transpose there and A transpose there. Multiply these two together. I'll put it right here. What would that be?
We got 3,
Uh-huh.
we got 2, so it was 5.
5? Is that what you said? Yes. Correct. Next.
That's 9 and 4. That gives us 13.
13. Next.
We got row 2, column 1. We got 5. That -2 gives us 3.
3. Is that what you said?
Yes.
Next.
And we got 2, 2. So we got 15.
All right.
And we got -4.
All right.
That gives us
11. Now what do you notice here? That AB transpose is the same as B transpose A transpose. Not the same as A transpose B transpose, but B transpose A transpose. See, this is that's totally different. These are the same. This is AB transpose is B transpose A transpose. Okay? Sort of. I don't know if you find it surprising or not, but anyway.
Is this always the case? Or
That will always be the case, as long as they're the right sizes to do it. If both of them are the same size square matrices, they'll do it. All right, here we have Vince. Just missing two today, Justin and Jordan, the two J's. Okay? Well, we got to, yeah. Okay. All right, you going to do another one? Okay. Find another one. Is that B? That was test 4. Here's test 5. Okay. All right. Throat is so raw feeling. Okay. Now, it says make a conjecture about the transpose of a product of two square matrices. Well, as long as the two matrices are the same size, then you can multiply them. And so the conjecture about the transpose of a product of two matrices is they're the product of the transpose of the two matrices, but in reverse order. Okay? Blah, blah. So let's do example 8 now. This is much simpler than what we just did. Find the transpose of each matrix. Here's A, I can't write, is equal to 2, 8. It's an 8, how it came out in A, I'm not sure. What is A transpose? That's an 8 at the bottom. Nope. It'll be 2, 8, but how?
It's going to be 2, 0.
No. 2, 8. The column becomes a row because you're interchanging rows and columns. So that first column will become the first row. Or, to say it the other way, the first row here becomes the first column, and the second row becomes the second column. So basically it's the same order, except it was a column vector, now it's a row vector. It exchanges columns and rows. This column became that row.
Who was the inventor of this theorem?
Okay. Believe it or not, there will be a purpose for this.
So who started this theorem?
They don't say. I'm guessing it may have been Cayley. He seemed to have done a lot of these things.
What was he thinking about?
Huh?
What was he thinking about?
Well, they didn't have anything else to think about. No, I'm sorry. I didn't say that. Okay.
You're right. You don't have to be crazy.
George Cayley, didn't he invent the glider?
What's that?
You know the guy who invented the glider, George Cayley?
This is William Cayley, I think.
William Cayley. Okay.
Yeah. All right.
Pretty sure he did.
Are they related, or they just have the same last name?
What's that?
Are they related, or they just?
I don't know. I would think they were far apart historically, so they may be distantly related, but I don't know. So here is matrix B. Matrix B is very creative. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right? What would be B transpose?
B transpose would be 1, 4, 7, then 2, 5, 6, 6.
Huh?
6.
No.
Oh, 2, 5, 8.
Ah. Next.
3, 6, 9.
Got it. Okay, there's B transpose. Okay. Now, I need some more room, so I'm going to clear the page. Okay to do so?
Yes.
All right. Here is C. 120, 210, 001. What will be C transpose? Somebody. What would be C transpose? 120, which way? Horizontally or vertically? Horizontal. 120, okay. Next, 210. Bless you. 001. What do you notice about that? Second? They are the same. You're absolutely right. Okay? We'll come back to that in a minute. Okay? Then let's do D. D is 01, 24, 1 minus 1. What would be D transpose? Which way are we writing that? Okay. All right. All right. Vertically. 01, 24, 1, negative 1. Perfect. Way to go. All right. Now, C was the special one there. And what makes C special? Okay? It is a special kind of a matrix, and it's called a symmetric matrix. And to be a symmetric matrix, well, the definition is A is equal to A transpose, okay, or C is equal to C transpose. It must be the transpose of itself. And from that definition, it should be clear that a symmetric matrix must be a square, obviously. And if A is Aij, then a symmetric matrix will be such that Aij is always equal to Aj for all i's not equal to j. Okay. That's part of it. This one happens to have only ones on its diagonal. Okay? It doesn't have to be. Okay? It does not have to be. Okay? But this one does. The other part of it, and this has to be, this is symmetric to that, that's symmetric to this is symmetric to that. Across the diagonal, they are exactly identical. Does that make sense? This entry must equal that one, this one, this one, this one. That's the same thing as saying Iaj is equal to Aija, you know, for that to be true. So it doesn't matter what the diagonal is. They could be anything. But to be symmetric, these elements have to be the same. Now I say that, they may come out with it, they all have to be one, but I don't think that's the case. All right. Now, and you see two things they've done here, that A to the N, they just did it and left it. And then they did the number of solutions. That was just thrown in here completely wacko, but there will be connections here. So let's now go to Theorem 2.6, properties of transposes. Now we've already hit on a couple of those, so let's hit on the rest of them. So here A and B are both matrices. Okay, they're both matrices, with sizes such that the given matrix operations are defined. I'll say of proper sizes, so that you can do the things you're telling them to do. Okay, C is a scalar. Okay? Then the following properties are true. If you have the transpose of A, and then you transpose that, guess what you get back with? Anybody? Help me. Anybody? Say again? I still can't hear you. ACP? ATP?
TT.
Okay. AT&T. Okay, no. You get back to the original A. Because you started with A, you transposed it, then you transposed it again.
I had a question for you. Go ahead and work.
Okay. All right.
Appreciate it.
All right. You get back to A. All right. Everybody agree? Second property of transpositive matrices. If you have A plus B, okay? Now you see in that first one, A can be any size whatsoever. Any M by N, it'll work. When you transpose it, it becomes an N by M. But then when you transpose it again, it goes back to being an M by N. And nothing changes except you just swapped everything twice and they came back where they were. This one, A and B have to be the same size. No matter what size they are, they have to be the same size. And then you transpose that sum. Here is what it comes out being. That's the same as A transpose plus B transpose. Okay, now wait, let's see if this makes sense. Let's say A is an M by N. B has to be an M by N. Otherwise you can't add them. You add them together, you get an M by N. You transpose that, you get an N by M. Well, if A was an M by N, you transpose that, you get an N by M. If B was an M by N, you transpose that, you get an M by N by M. You can add those two together, and you're going to get an N by M. The sizes work. This tells you the numbers work as well. Okay. Now, part of the reason for that, a little bit of it, is it doesn't matter which order you add matrices. It matters which order you multiply, but it doesn't matter which order you add. So you could have added these in this order or that order, and you could have added the transpose in any order because it doesn't matter. So there, the order, what you say first, A and B, doesn't really matter. All right, the third one. Excuse me. If you have C times A, and you do the transpose of that, that's the same as C times A transpose. Now, why would that be the case? What does multiplying a matrix by a constant do for you? What do you physically do? Huh?
Scales it, doesn't it?
Okay, how do you mean that?
Like it multiplied by 2, you scale the values in the matrix up by 2, right?
Okay. In a sense, yeah, but what? This is a matrix now, not a scalar. I mean, not a vector. Vector, I think of as scalar. Okay. Now, I don't know what that means for a matrix. But what does it mean to multiply a matrix by a number C?
Multiply.
Every element in A is multiplied by C, right? So, and then you transpose it, you just exchange the rows and columns. Well, if you transpose the A first, you exchange the rows and columns, but then you're still multiplying every element by C. So sure, that's going to be the same thing. Exactly the same thing. All right, number 4. And this is the one we did in the discovery. If you do the product A times B and transpose that, does anyone remember what the answer was? We did it in the discovery problem. It's what? Not really. We did it in the discovery one. No, we tried that and it didn't work. B transpose A transpose. Remember, you have to not only transpose each of them, but reverse the order. That is the case. See, in addition, it doesn't really matter. But in multiplication, not only do you transpose of a product is the product of the transposes in reversed order. You have to have the reverse order there. Okay. So we can extend that second one to be more than one matrix. Okay? For instance, what if you had the sum of three matrices? A plus B plus C, that's a capital C, not the same as our constant C, and you were transposing that, then this would be A transpose plus B transpose plus C transpose, because it doesn't really matter what order you do the things. Okay? But now number 4 also extends, but be careful how you extend it. If you're multiplying three matrices together, A times B, and then multiply that times C, or in any order that you multiply. Of course, these have to be the right sizes to do so. And then you transpose that. What would be your guess of what the answer is? Anybody? Anybody? A little louder.
Would it be C again? B transpose A transpose C?
Say that one more time.
Would it be B transpose A transpose C, or would you flip the order of all of them?
You have to reverse the order. So what would it be? C transpose, B transpose, A transpose. Perfect. And part of the reason is, if you think about it, the sizes are here. So if this is an M by N, this has to be an N by something. So that we call it N by P. And C has to be a P by something, call it Q. Okay? But before you can and you transpose those, then the product of these would be an M by Q. Yeah. M by Q. When you transpose. Now, when you transpose, that becomes a Q by M. Well, then you got to lead with the Q here, so you got to transpose the C and make it a Q by P, and then multiply that. You have to transpose that because these two middles are the same. So you see, you've got to do it that way just to keep the sizes right, and then it happens to be it keeps the numbers right as well. Okay. So let's see if we can do example 9. Do we have time? Anyone got the time? Second? 46? We've already gone over, haven't we? Yeah, okay. We'll pick up with 9 next time. Homework exercises here. Do any of the odds 1 through 5, any of the odds 7 through 11, any of the odds 15 through 19. Do number 21, 23, 25, 27, any of the odds 29 to 33, 35, 35, 37, either 39 or 41, or both if you choose. Okay, we'll leave it like that and do the rest of these later. All right, good deal. Huh?
I have a question.
What's that?
There's this matrix I'm having trouble with.
The what?
I have a matrix that I'm having trouble with.
Okay.
I'll give you the numbers.
What's that?
I'll give you the numbers so you can help.
Okay. What are they?
2.
How big a matrix is it?
Is 2 by 4.
2 by 4.
I mean 3 by 4. Sorry.
3 by 4. That size?
Yes.
Okay, and what is it?
It's 2,
2,
3,
3,
1,
1,
10.
10.
Then I have 2,
Second?
2,
2,
negative 3,
negative 3,
negative 3,
negative 3,
22.
22.
4,
4,
negative 2,
negative 2,
3,
3,
negative 2.
negative 2.
First thing I did, I did negative row 2
Okay,
and added to row 1.
okay. Now, this is a homework exercise, a test problem, right? Okay, I don't usually do test problems. But let me just tell you what you're trying to do there. You said you did,
I did negative row 2 and added to row 1.
okay. And where did you put that?
I ended up using that as my second row, but first I wrote it down as my
Okay, but it becomes your second row.
yeah,
That's an okay move for your first thing there, yeah?
So, and after that I did negative 2 row, no, negative 1 half, negative 1 half row 3 added to row 2. That became my row 1.
And that becomes your new row 1?
Yes.
I wouldn't do that. Because what you want is a 1 up there in the upper left corner. And what you just did gave you a 0 up there.
Because it's negative 1 half.
I thought you said negative 1 half row 3 added to row 1.
No, add to row 2.
Oh, row 2. After you did the other one? Because the first thing you did, put a 0 there at the first element in row 2, right?
Yes.
Okay, if you do that, then you lose your 0. Not a good idea. Okay, now what you started off doing was okay. You don't have to get the 1 here first, so that's really what you want. But this will be awkward here, so you could do manipulations to make that a 0 and then to make that a 0. That would be using row 1 to make that a 0, right? And then once you do that, then you can divide by 2 and make that a 1.
But I'm having fractions in there.
I know, you're going to have fractions. This one, there's no way around it. Frankly, no, there's just no way around it. And live with them because they may work their way out in the end, but there's no way around having fractions somewhere in the middle. What you were doing was avoiding fractions for 2 steps, but then at some point you're still going to have a fraction.
They showed up.
Huh?
They showed up at the end.
Yeah, they will, but at least you avoided them for 2 steps. Okay. So it sounded like you were proceeding correctly there until you started trying to do and move back up again. Then you start losing the zeros
Can
you
you
had.
look at this and see if I'm going like this?
What's that?
Can you look at this and see if I'm going somewhere? Or should I back
What's that?
up? Am I going somewhere or should I back up?
Okay. How did you get from here to here?
I did this.
Okay. I can see where you did something here and got zeros here. How did you get a 1 here?
By dividing 1 half to row 4. Row
Okay,
2,
right.
and then adding it to row, with row 3, adding it to row 2 give me 1.
To row 2. But then you moved it up here?
So my row 3
No.
became row 1.
Okay. Well, how did you get a 0 down here?
So this row 1 became my row 2, and row 2 Because and row 2 become my row 3. That's because I divided row 2. Row 1 by 2.
Now, here's what I know would have been legal. If you had moved this one up here, moved these down here, however you wanted to, then divide this by 4. That would have worked.
Actually, that's exactly what I did.
Okay.
That's what
But
I
you
did.
did get it right. Okay.
Yeah,
You did get it right.
I did. That's
Except
what I
that-
did.
Yeah. Okay.
That's what I did.
Okay.
I just didn't know it. But that's exactly what I did.
Right.
I divided by 4
Yeah,
and 1.
and moved it up there, right.
That's what I
So
did.
far that's legal. Everything looks all right.
So,
I haven't checked the math in them, but if you did the math right, that should be it. Okay.
okay.
All right.